spent a year trying to write a book sort of about this type of education. So I wrote the 200 pages, and then I was bored to tears. So this past year, I went back into teaching to do some more research on how the human brain learns. And next year, I'm teaching a group of high school seniors the neuroscience of learning. So this has been my obsession since I set foot on this campus in 1977. And I think there's almost nothing that I'm saying today that I could have said in 1977 because the field of cognitive neuroscience has changed so much that there are probably about 4 sentences that were true in 1977 that we now know today. It's constantly changing. The way I got into understanding the neuroscience of learning is from that first moment I walked onto this campus and saw these bright kids, these happy, motivated, athletic, artistic, creative, scientific, mathematical kids, brilliant, who didn't read well at all. And it leads you right into the big questions of how do brains work? And how can this be that this kid can be so good at these things and actually so bad at some real academic things like reading? So what I did is started investigating. And so I investigated by teaching children at the Carroll School and also by reading. Back in 1977, none of these books, except for the one on the bottom right, had been written. This field is incredibly new. Really in the last 30 years, there have been huge breakthroughs, which I'll talk about in a bit. But this is my bibliography put up front for you. Parents, start in the top left of this slide. Best book written on dyslexia and reading difficulties. Worst title of any book. Because you don't want to overcome dyslexia. You want to learn to live with it and harness it and actually end up making it your advantage. So publishers probably got the Shawitzes to use that title, but it's the wrong title for a really brilliant book, updated just recently. Second one is The Dyslexic Advantage, which is the good side, the positive side of learning differently or being dyslexic. And it's vignettes about very brilliant, successful adults who all had, I think, probably the same set of circumstances that your kids have, because that's why you came to Carroll Summer School. Some of these next ones along the top are getting more deeply into the neuroscience of it, a little bit nerdier, a little more egg-headed. The book that I wish I had written in the bottom left here, NeuroTeach, is pretty accessible. You don't have to be a neurologist, you don't have to be a teacher. Sort of how it's the story of how does maybe this talk this morning have any real implication for your kids? When you walk into the next IEP meeting or case conference for your child, I think NeuroTeach has a lot to offer. I hope today's talk has a lot to offer. Culturally Responsive Teaching in the Brain is a great book written by Zaretta Hammond, sort of looking at the way schools are unequally organized depending on wealth and race and all sorts of things. Really brilliant. She uses a lot of neuroscience in that. David and Goliath by Malcolm Gladwell is the book you can buy at the airport. Just really interesting. And he uses dyslexia as the David and Goliath story. So the dyslexic is David up against the monster of education, and David wins. Really good. Fortune magazine, a couple decades ago now, the dyslexic CEO, and looking at Charles Schwab and Richard Branson and a bunch of others, could be updated beautifully. And in the bottom right is a book written in 1932. All these others were written in the 21st century. This is Dr. Samuel Torrey Orton, of the Orton-Gillingham method.
Could you try again?
Yeah, so, you want me to say that all again? I'm really up for that. And to realize that almost 100 years ago, neurologists were drawing pictures of brains on the front of that. You probably can't see it too well. I'll just stop talking. We'll see what happens. This book is called Strephosymbolia, which means twisted symbols. We now call that dyslexia. But in 1932, he was drawing pictures of human brains to describe the reading difficulty. So, when we teach chefs and nutritionists, we teach them about, this is audience participation part, we teach them about food. When we are teaching dentists, and in this case probably orthodontists, about teeth. Thank you. Very good. When we teach engineers and mechanics, we teach them about engines. When we teach teachers, we teach them about children. Right. But when we teach teachers and parents about children and learning, we don't tend to teach them about brains. This afternoon, I'm talking to a group of teachers here at Carroll and try to take them deeper into understanding the machine, the food that they're working with. And teacher education programs and parent education programs very rarely talk about how the brain learns. So we're going to do what would take about probably 5 college courses in about 35 minutes, which we're going to go into looking at the brain in more detail. We're going to talk about neuroplasticity. Do you know that word? I have this indelible memory, and it was actually in this room, where I said to a group of parents, maybe 20 years ago now, how many of you know the word neuroplasticity? And like, you get a couple sheepish hands coming up a little bit. And there was one parent in the front row who said to me, yeah, I know about neuroplasticity. I'm counting on it to save my child. So today, this is how far the field of neuroscience has come. A lot of people understand what that word means, and it has huge implications for education and parenting. We're going to talk about emotions and cognitive components of the brain, how our emotional life and our thinking, cognitive life are inextricably related. You cannot separate the two of them. We're talking about how the brain learns to read, which I think is probably topic number 1 for all of you. Yeah? And then just to touch on math in this short talk. And then finish up with what's learnable and what's remediable. What can you actually expect to change in your child so that they are a better student? There are other topics here: cognitive intervention, neurodiagnostics, neuroprediction, which we don't really have time for, but I'm happy to talk to anybody about those things anytime. It's also important to point out there's a lot of neuro nonsense out there, a lot of things that are out in the popular nomenclature, in pop news, that are just plain wrong. First one is that human capacity is unevenly distributed, kind of in a bell-shaped curve. That over here we have the very smart kids, over here we have the not very smart kids, and this huge component here in the middle is sort of the middle 65% of humanity. And so that when a teacher walks into a room, they might expect a few brilliant kids, this side, a few brilliant kids, a few not very brilliant kids at all, and then just a whole bunch of kids in the middle. And it's absolute nonsense. It's just the way an IQ test works. It was designed to distribute the human population. Neuroplasticity would tell us not to believe that for 1 single second. All human beings have the capacity to do school-level work at a high level. The second one is there's something called a preferred learning style. Don't believe it for a second. Well, my kid's actually a visual learner. They tell me that my child learns best when listening. Those things are probably somewhat true. But every single brain has the capacity to do auditory work, to listen, to do visual work, to see, to do tactile or hands-on work. And teachers who say, well, I teach to an auditory, teach to a visual, are missing the fact that there is this whole brain. Don't buy that for a second. We're either left-brained or right-brained. Wrong. Left brain means we are either logical, or right brain means we are creative. We are both. And in fact, the human brain can't work with just half the brain. And there are some things called hemispherectomies where brains have to be removed to avoid epileptic seizures. And that's a whole different story. But we are a whole brain. Exercises. Lots of schools hire occupational therapists. And when you come in and you realize that the child's not succeeding too well, they say, well, we'll build some OT into the IEP. It's not going to help your child learn to read at all. There's nothing to do with it. Stimulus-rich environments. Make the place as vibrant and colorful as you can. No, not necessarily a good idea at all. And the last two are sort of about diet, and there's no evidence actually in the literature that sugar makes you go attention crazy, or that omega-rich foods are going to make you a better learner. So this is from an article, 2012, on neuromyths. And a lot of people say, well, we just don't know enough yet about the human brain to have any implications for teaching. Wrong. We do. We know this. Neuroplasticity. This is probably the number one take-home message from this talk this morning. The human brain has enormous capacity to grow and change. As an Orton Gillen hammer myself, breaking words down to their components, neuroplasticity is a cool word, really good at the cookout this weekend. Throw it around, people think you're smart. Neuro, brain, plastic, meaning bendable, flexible, and itty, the state of being plastic and flexible. Our brains, human brains in particular, have amazing capacity to change. So you have a 7, 8, 9, 10-year-old child with a diagnosis of a reading disorder, dyslexia. That is not a prediction at all on their future. It is not a limitation on their capacity to learn to read. Neuroplasticity is the gift to dyslexic children. So let me explain. Maybe. So here's my metaphor, and I think this one really works in terms of understanding neuroplasticity. When we are just beginning to learn, the neurons, neural brain cell, neural pathways are like a path through the woods, which is beautiful, and if it isn't walked on a lot, what's going to happen? Things are going to grow over it, and it's going to be harder and harder to find, and eventually it might disappear. Things in our brains that are sort of learned are like that pathway. But we've already covered that. I don't understand why this child doesn't understand it. We've covered it. Well, you've covered it sort of like that. And if you haven't covered it better than that, something else is going to cover it. Weeds and vines and grass and all sorts of things. This might be a more developed brain pathway or network, which has a greater chance of existing over time. So the first one could grow over pretty fast, right? And that pathway is gone. The second one, it's going to take a longer time for that to grow over. But it still could happen, right? That's not enduring for sure. This one, that's got a chance of lasting a long time and eventually turning into a superhighway. So the reason why this metaphor really works for me is that's beautiful. And there's a lot about the dyslexic brain that's beautiful. It's more developed, and it's a metaphor for learning, something that's introduced, something that's sort of understood, something that's mastered, and then something here that becomes virtually automatic. And that's what learning is. That's what teaching is. And the metaphor works because also this has got a lot of electricity in it. And these pathways in our brain are really transformation of electric energy and also chemical energy in another way. Another, I'll show you this. Will this just work, do you think? Look. This is a really quick video.
Not so long ago, many scientists believed that the brain did not change after childhood, that it was hardwired and fixed by the time we became adults. But recent advances in only the last decade now tell us that this is simply not true. The brain can and does change throughout our lives. It is adaptable, like plastic. Its neuroscientists call this neuroplasticity. How does neuroplasticity work? If you think of the brain as a dynamic, connected power grid, there are billions of pathways or roads lighting up every time you think, feel, or do something. Some of these roads are well-traveled. These are our habits, our established ways of thinking, feeling, and doing. Every time we think in a certain way, practice a particular task, or feel a specific emotion, we strengthen this road. It becomes easier for our brains to travel this pathway. Say we think about something differently, learn a new task, or choose a different emotion. We start carving out a new road. If we keep traveling that road, our brains begin to use this pathway more, and this new way of thinking, feeling, or doing becomes second nature. The old pathway gets used less and weakens. This process of rewiring the brain by forming new connections and weakening old ones is neuroplasticity in action. The good news is that we all have the ability to learn and change by rewiring our brains. If you have ever changed a bad habit or thought about something differently, you have carved a new pathway in your brain and experienced neuroplasticity firsthand. With repeated and directed attention towards your desired change, you can rewire your brain.
Here we go. No need to worry any further. So I hope you can sort of hear that. Can you do it in the back a little bit?
Not so long ago, many
The capacity to carve new pathways in our brain. That's really what neuroplasticity is. And when I'm working with teachers, I say, that's your job. The job of the teacher is to help students carve enduring pathways that have some positive value. And so for the purpose of reading, if your child doesn't have a great pathway already, or a network of brain cells called a neural network, if that's not in there, teachers have choices. Bypass it, don't make them read. Get an IEP that says, don't make this child read. Not a good solution. An accommodation. Don't have this child read out loud. Don't have this child in a fast reading group. Don't have this child embarrassed by having to read in front of other kids. Yeah, that's humane. Or to carve new pathways. The science of reading. And that's really where we want to be today. Another metaphor, very quickly, thread turns into string, turns into rope, turns into better rope, turns into cable, turns into cable that's capable of transmitting electric signals. That's the job of a teacher. It's also what we do as parents. Try to help kids develop enduring pathways that encourage positive outcomes. So, what do you need to know? And this is sort of your take home. With more time, we'd have a conversation right now, but I'm sort of thinking we don't have a whole ton of time. So, the brain a child's born with will evolve, develop skills, and get good at things that were previously weaknesses when it's nurtured and challenged properly. A teacher's job is to harness neuroplasticity to build capacity in children. Just quickly on this one. This is an issue that in my career I didn't really come to until later, because I thought if, from a cognitive perspective, if I could teach these children to read, they'd become happier. It's true. But the reality of the way the brain is structured, they're not going to learn how to read if they're not feeling safe and secure and happy, and if we don't have trusting relationships. And so the human brain is designed in this way. So at the bottom, the base, the brain stem, we are reptiles. And we are just designed to protect ourselves from threats. In the middle, sort of up in the middle of our brain, inside, we are mammals. We are limbic systems. We are like our dogs and pets, cats, where emotions drive so much of our capacity to respond. And at the top of our brain, this great big neocortex that humans have, these huge heads and skulls that we have, is where our logic and thinking is. When kids are scared, they go what's called subcortical. And reading, for example, which is in first and second grade, the smart kids know how to read. The sort of smart kids, and the not very smart kids don't. What happens to the dyslexic kids is they drive right down into their limbic system and maybe even into their reptilian brain, protect and defend at all costs. And you get all sorts of behaviors to avoid humiliation. So instruction has to be emotionally sound. Of all the applications of neuroscience, this is the one that I'm able to talk to kids about. And I talked to my 8th graders about it this past year. When you're facing a new task, it's kind of intimidating. And it's metaphorically like looking into a pit. And don't fall into the pit. The smart kids don't fall into pits. If I fall into that pit, everybody's going to know I'm not a smart kid. The reality is, all kids facing a new task fall into a pit. And discussion of the learning pit is about the best way to respond to the emotionality of learning. To say, we all fall into this pit. And then we figure out how to master the new task and climb out of the pit. So we have to understand, no matter what we're doing, that we are emotional beings, and the big human neocortex shuts down if we're scared or feel a huge threat. So teachers need to help kids climb out of the pit. Don't be despaired that you're in the pit. Even the smart kids fall into the pit. They're just good at getting out of it. There are skills and strategies you can learn to get out of it. That is not nearly enough on the topic of emotionality and learning. A core principle at Carroll is that instruction has to be emotionally centered. For all the great skills that these tutors and teachers have to teach children how to read, if they don't have the ability to create a safe environment and a trusting relationship, the learning of the sound symbol of the code of reading, it's not going to happen very well. Has to be safe, has to be okay to take risks, has to be okay to fall into the pit and learn how to get out of it. Have to be with a peer group where you look around and go, these kids are like me. And that's a smart kid. And that's a funny kid. And that's an athlete. And that's a dancer. And that's an artist. I like them. And they're smart. And I'm smart. Got to do that. And that high effort success is likely. If I'm going to put in this effort, there has to be a high likelihood that I'm going to be successful. Otherwise, I'm going to engage in low effort failure. So the emotionality of all this is hugely important. All right, let's go for about a half hour here of how the brain learns to read. And it's really a fascinating story. So you'll notice the date on here, 1989. That's about when we started to see brain imaging. That's not very long. That's how new this science is. When I started at Carroll, people didn't talk about any of this stuff. The top left is the brain lighting up listening to words. So if I could just orient these images, they're like this. This is the left hemisphere, front of the brain, back of the brain. So when we are listening to words, something sort of logically up above our ears lights up. And the hotter the color, the more activity there is. So the reds and the whites are where the most activity is. Bottom left, when we are producing words, the activity moves from here towards up here, towards the frontal lobe. I'll get more specific about this in a second. Bottom right, when we are associating words, doing rhyming, and trying to think about what's another word for a car. That starts to move very frontal into the front of our brain and this great big, uniquely human component of the brain. And in the top right, when we are reading, the activity goes very much posterior to the back of the brain, to the occipital lobe. At the very beginning of reading. We're going to go in more depth in a minute. So this was a cataclysmic slide in the field of education. No, it wasn't. Most educators didn't see this. Most educators didn't know this. And so back to my very beginning, when we're teaching teachers, we need to teach them about the brain. Teachers need to understand this kind of thing. So let's add some detail to this now. This is what it looks like today. This is neuroimaging 30 plus years ago. This is neuroimaging today. This is Mass General Hospital's, you know, the Genome Project? This is the Connectome Project. How do neurons connect within the human neocortex, this big human brain? And each of those fibers are strands of neurons that are connected to each other, like a road, a pathway through the woods getting stronger and stronger and stronger. And what they're trying to do now in the Connectome Project is understand the function of each of these connections. And they understand some. And I'm not a neuroscientist, but as an educator, I understand some of them. And as parents, I want you to understand some. So what the Connectome Project is trying to do is understand strong pathways in the brain. So again, left hemisphere. In the back of the brain is the occipital lobe, where the child opens up a book, is beginning to read, sees those squiggles on the page. Uh-oh. Activity in the back of the brain. It is initially a visual task. Then I see a letter. I think I know the sound that letter makes. The activity goes from the back to here. I'll give you the real neuroscience terms in a second. Something, some band of neurons needs to be able to connect what we're seeing to what the sounds are. Right? Just very beginning phonics. If I can see it, if I can think about the sound it makes, then I go up into this part of my brain where I'm trying to put this together. And because we know all letters don't make the same sound in different circumstances in a word, like vowels can make all sorts of different sounds. You need to be able to do some integrating of, based on where I see this letter, it's going to likely make this sound. And then we say the sound. So is there a band of neurons that connect these things up? If this is just the very beginning of phonics, like preschool, first grade, what they're trying to, I have a 4-year-old grandson, what they're trying to teach him right now. Unbelievable, they're teaching 4-year-olds this, they shouldn't, but they do. What sounds do letters make? So there's got to be a pathway there. So I've drawn it in here in green, but you can sort of see it a little bit in green, a light green, that there is some sort of a pathway that connects these things up. So this is a very cool slide that shows a young man in a neuroimaging machine reading a word. So I'm just going to let this run for a little bit. So these are milliseconds, and it starts in the back of the brain now. It starts in the back of the brain now. So what do you see in terms of direction of the activity here? Back to front, right? Back to front, back to front. We're going to come back to this one in a second. The yellows would be even hotter colors, and so representing even more brain activity. So we see some things down here, sort of in the, where we're hearing things. We see some up in the front, where maybe we're saying things. He's reading the word cat, and it makes me nuts that he's reading the word cat, or that some neuroscientists thought that was a good word to choose. Cat's a terrible word to choose to teach kids phonics. And the teachers and tutors who are working with your kids this summer know better than to do that. Like cat in the hat would have been much better as bat in the hat, with what are called unequivocal sounds. C is a nasty sound. Right? C can say k, C can say s, C can say ch, C can say sh. So that's the level of sophistication that actually reading teachers need to have, that Orton Gillingham trained teachers do have, and most reading teachers in America don't have. And the way the brain responds to a reliable sound, like boop. In English language, the letter B makes one sound. Boop. It can be silent sometimes, rarely. But that's the sound it makes. That would build a pathway through the woods. It is much easier to maintain in less time. And what does the child learn? There's some reliability to this crazy squiggle on the page thing. I feel safer knowing that there are unequivocal sounds. Anyway, that is a digression on my part. So now we're going to put the neuroscience words to this. In the back of the brain, we have the occipital lobe, which is the visual cortex. Pretty well established, that's what the back of the brain is. On both the left and right sides. My slides are on the left side. Do you know why? Initially, but not totally, initially reading is a left hemisphere activity. The decoding part of it. Incredibly quickly, in milliseconds, the right hemisphere gets involved. But for the beginning of reading, the decoding, you see the squiggle, you recognize that squiggle. It's a circle with a stick on it, which is also nasty because it might be a D, that's a circle with a stick, a B, it could be a P, or a Q, or a 6, or a 9, right? So the pathway will be built with reliable, consistent, let's do B right now, not D. Don't bring in D until much later. So the frontal part here is this great big human IQ of ours. Other animals really don't have foreheads much to speak of. They really don't have frontal lobes much to speak of. Like my dogs, above their eyes, the skull goes pretty much straight back. And you kind of see that in their behavior. Other animals that humans think are smart have sort of frontal ridges and things. Our primate cousins, chimpanzees, monkeys, apes. Dolphins have a little, if you can visualize it, a little ridge, a little frontal ridge. You tend to think dolphins are smart. Back here, the parietal lobe, this is integration, sense of time and space, orientation visually and spatially on a page, for example. Back of our brain and visual cortex. And here, sort of above our ears, is the auditory. Those are the technical words for these major lobes of the human neocortex. If I go too fast and people are trying to capture slides, just let me know. The dyslexia research is very interesting in the areas where I have put the yellow lines, called convergence zones, where the functions of the lobes come together is where the greatest differences in the dyslexic brains are from normal born brains. Get that? Normal born brains. The fact that they're typical doesn't mean they're better. It just means they're typical. So we want to look at those convergence zones. So this first one, where what we see meets what we hear, where the occipital meets the temporal, is what's called the visual word form area, or the fusiform gyrus is the technical term, where squiggles on a page. I recognize a squiggle, and I've got a sense of the sounds of things. That's that convergence zone. Activates very differently in the dyslexic brain, in the untrained dyslexic brain, in the dyslexic brain that hasn't had an opportunity to build the pathways yet. Neuroplasticity tells us that we can build that pathway. The second convergence zone is at the top of our temporal gyrus, called Wernicke's area, which when you read Overcoming Dyslexia, the Shaywitz book, they take you into this in great detail. But the top of the temporal lobe is where sounds and symbols get connected. And it's called so many different things, but the superior temporal gyrus is one way of thinking about it. And it is an area that is so underactivated in early dyslexic children. What's the job of the teacher? Get that to activate. And the third one is the inferior frontal gyrus, about here, called Broca's area. And we've known about Wernicke's area and Broca's area since the 1880s, based on brain injury, soldiers who got shot and lost the ability to do certain things. But it's so interesting that this is called localization theory, kind of old school, that there are parts of our brain that specialize in certain functions. Modern theory is not about localization, but it's about network development, or the connectome. And the ability to connect these things now. And I've put that same green line in there. Oops, I'm going the wrong way. Don't do that. Sorry. I'm totally going the wrong way now. Shouldn't do this. Bad idea. It's that area that we're looking at. Okay, take a break mentally for a second while I go back. Okay, so that's supposed to be the same neural connection, the same network. And the job of teaching reading is to wire those things together. It's got a fancy name, the arcuate fasciculus. But it is the major channel that you see here. Starting right now, you can see the energy going sort of in that arcuate fasciculus. That's what you want to wire together. And the research says in the dyslexic brain, that network is not well developed at all. Can it become well developed? Absolutely. I want to show you one more thing on this. So we do see, starting now, the arc up, now. You also see something inferior. So in neuroscience, superior only means higher in the brain, and inferior means lower in the brain. It's not a value judgment. So there's a superior pathway, the arcuate fasciculus that we just talked about. Connects what you see to what you hear to what you say. There's also an inferior pathway, which is really something that we're working on in cognitive development at Carroll, which is what you see to what it means. And actually, both of these pathways need to work simultaneously. So let's look at some early pictures of typical brains versus dyslexic brains, and then some images of neuroplasticity. So neuroscientists do something nasty to we mortals, which is the left is on the right, the right is on the left. Why do they do that? Well, what they're doing is they're taking a brain and they're splitting it open like that. So you end up with things on the wrong side. At the top is a normal reader. And we see in the left hemisphere activation in those three convergence zones. You can sort of visualize it. Community service announcement. Not all brains are organized exactly the same. Not all faces are the same. In fact, they're all different. All brains are slightly different, but we all have signatures of faces. And brains have the same kind of localization, but they're all slightly different. So when I show you this, and those marks are orange and yellow marks aren't exactly where I showed you before, it's just because brains aren't all the same. So we see an activation in yellow here in the visual word form area. We see activation up here in the superior temporal gyrus. And we see activation in the front and the inferior frontal gyrus. And on the right side of this normal reader, we see some activation in the right hemisphere. Drop down to child with reading difficulties. In the left hemisphere, on the right side of the slide, sorry, you see much less activation where there's supposed to be activation while reading. And on the right side, you see a great deal of activation where there's supposed to be less. This slide is likely evidence of a bright child who doesn't know how to read yet, has not developed those pathways, but a smart kid trying to figure out, what the heck is this? Well, we've been reading about animals and pictures of an elephant, so maybe. But it's not really reading, it's good, what's called psycholinguistic guessing. So this is a good slide. I don't love it because it perpetuates a neuromyth. The dyslexic kids do things backwards. This slide sort of is backwards. That's a neuromyth. Dyslexic kids don't do things backwards. We all do things backwards sometimes. So this next one is the same child, the top in kindergarten. And where the green arrows are, you see underactivation and lots of activation in the right hemisphere. This time, left hemisphere is on the left, right hemisphere is on the right. But this is a child, in the date 2006, we start to see these images, of a child who has learned to rewire in a typical fashion. And so we're seeing where the green arrows are, activation here in the superior temporal gyrus, sound to symbol, and activation here in the output. And we're still seeing a lot of right hemisphere activity. So I have sent this underlying message to you all around. Difference isn't bad. Difference may have advantages. A book called The Dyslexic Advantage. There may be great advantages to this first grader here who's learning how to deal with the sounds and symbols and have a really active right hemisphere. Don't silence the strengths of dyslexia. Encourage them. Here's another study which came out of National Institute of Health. Neuroimaging allows us to observe changes in the neural structure of the language centers in the brains of dyslexic children. Left is on the right, right is on the left. At the top is before, and so the white blobs here in the left hemisphere are in places you want them to be, but they're not very well developed, and the right hemisphere is sort of overdeveloped. Same child after, you start to see a much better pattern. What this says, which you cannot read, is neural systems supporting reading may not be fixed in place. It's about a 25-year-old slide. We can now say definitively, they are not fixed in place, but develop if challenged. Shown is an image of a 10-year-old with severe reading disabilities, at Carroll School we'd say differences. Before and after, you'll load this, 60 hours of intervention. 60 hours. That's unbelievably little time to see a neural change of this magnitude. After 60 hours of intensive instruction, during which the child rose into the average range in reading speed. The before image captures the brain exhibiting the standard activity pattern of children with reading difficulties. The after image shows increased activity in the left hemisphere, a pattern consistent with non-impaired readers. Neuroplasticity in action. This can happen when your children are in the hands of people who actually understand how the brain reads and how the English language is structured. So fast forward several decades, we also cannot be quite so definitive that a well-remediated dyslexic reads the same way as a non-dyslexic. Modern research, which I don't have time to get into today, is saying there are real differences in a well-remediated dyslexic. I'm not making eye contact with some of you I know well who are very well-remediated dyslexics, who do not read in a typical way, but are highly successful readers and get tons of comprehension from that. So, but we do want to make sure we have these patterns. So, what do you need to know? Some brains are pre-wired to be pretty good at reading. Other brains are not. But the brain can learn to wire together different functions necessary to become a strong reader. Neuroplasticity is our friend. Knowledgeable teachers know how to rewire their students' reading brains. Just a word on math. We've already talked about the letter B. What does that mean? What does the letter B mean? Good answer. It doesn't mean anything. It doesn't mean anything in the context of reading. It is a symbol that the brain is supposed to connect to a sound. So we need to teach those sound-symbol relationships in a very rote manner to build the pathway. What does that mean? Here you have some answers, right? 3 little pigs. 3 in all languages, all cultures worldwide. 3 items. A triangle. Math should be taught with a symbol meaning connection. And it's really hard for a lot of people who are trained as reading teachers to teach math properly. And so is dyslexia a reading problem? Technically, yes. But what underlies the reading problem can also be a math problem. Math is taught without the meaning component in the primary position. Neurologically, doing computation follows that same pathway we've talked about. The meaning component is an entirely different fasciculus, which is really connecting visual right up into time and space. It's just an editorial comment. Connecting left and right. Is math a left hemisphere activity? No, it's much more a combined left and right. Now I'm going to finish up really quickly here. So here are some big questions. Is a child's learning profile his learning profile for life? Audience answer, no. What constitutes meaningful progress for each student? Is it MCAS? Is it how many pages in a textbook have been completed? How many worksheets are done? No. What is remediable? That's a really important question for parents, for kids, for teachers. What can you actually address? Where can you build pathways for kids? So I've pushed that you can build pathways for reading. I have pushed the superior fasciculus network. Research is saying there are also many issues that create the reading problem that are different from phonics. This is a phonological pathway. There are many other pathways that need to work efficiently for reading. What is remedial? Can all students become strong, fluent readers? When I started at Carroll, Carroll was great at teaching kids how to decode, but it wasn't very good at teaching them to be fluent readers, easy readers. We could solve the decoding problem. We didn't know enough back then to say there's much more to it than that. Can we build efficiency in our students, or are they just destined to be painfully slow readers right through high school, college, wherever they choose to go in life? What underlies this thing we call dyslexia? What sort of other cognitive thinking issues, brain-related issues relate to this? And these are questions that Carroll Schools started taking on about 20 years ago. What else is there? So we started doing all sorts of testing and poking and prodding on our kids. And initially, it's gotten much more sophisticated than this in the last 20 years, we found that our kids were really bad at some cognitive tasks that are necessary to be good readers. So the question is, what's remedial? Could you teach kids who are just really slow at reacting to squiggle? They're just slow at it. In fact, they were slow at reacting to all sorts of visual input. Could you teach them to be better than that? Faster than that? Would that help them become better readers? And likewise, issues of executive function, how they take on a task, how they execute a task. Could you improve processing speed? Like, how many of the evaluations in your kids say slow processing weak working memory. Can you improve those things? Is there something schools ought to do to improve those underlying skills that support reading? If you're not going to be a good reader, if you don't react quickly to the visual input, if you can't process it quickly, if you can't hold on to that information with the memory while you're reading, doesn't matter how good your phonics are, you're going to be a good decoder, but you're not going to be a strong fluent reader. So we started looking at these issues really carefully about 20 years ago and said, okay, we don't have the expertise as a bunch of good, caring, loving teachers. And we started grabbing people from this incredible research community in Greater Boston and really glommed on to John Gabrielli at MIT and his research into how the brain learns. We looked at, and I forget now, Ben and Jen back there, how long ago this was, but maybe 15 years ago, roughly, 10 years ago, Jen says, where we looked at 386 kids, a good, strong population, and what were the Carroll student body particularly bad at? And we're more sophisticated in this today, but those are the 4 categories we looked at. We've subdivided those now into many other. But 60% of Carroll School students were woefully bad at reaction time. So the research question, run into MIT and ask those folks, the neuroscientists, can you improve reaction time? And they said, you ought to be able to. And we went about the business of doing that. So yeah, 8, 9, 10 years ago, we looked at whether we could improve cognitive skills in kids. So in the fall of 2013, in orange, these are kids who had multiple cognitive deficits of the list that I just showed you. In the yellowish, they had one major cognitive deficit, statistically significant, and in the green, kids who had none. How do you end up at Carroll School? Loving parents who were unwilling to just let failure occur, they're battlers, they fight for their kids. You end up here because you have multiple cognitive deficits. If you were an easy to remediate kid at the public schools, regular parochial and private schools would probably do okay. You end up here because there are multiple underlying causes of this reading problem. Could you improve that? So we did a whole bunch of cognitive activities. And in the middle bar here, wow, we greatly reduced the number of kids with multiple issues and greatly increased the number of kids who had no statistical cognitive difficulties underlying. And then on the far right, so we got excited about this and said, there are things we can do to improve what's going on. And sort of the final metaphor is, you can't build a house on a weak foundation. You can't teach a child to be a good, strong, fluent reader with a foundation that is full of cognitive deficits. And so modern, I think, 21st century remediation goes for the whole brain and for the underlying causes of what's going on. So skills that underlie academic achievement are not well understood in most schools. Yet teachers understand these obstacles and seek to remediate the underlying cognitive skills, get way better results in their kids. Okay, we should stop there for Q&A. How are we doing with faithful time? So I just threw a ton of stuff at you. Little tiny pathways through the woods. Did anything stick? Questions that you have. I really put my bibliography up front because that's how I learned all this and looking at kids and learning. Start reading. Yeah.
So you're obviously very passionate and taking time to learn this. How much of this is taught to either regular teachers or teachers that have the working, working people? Those kind of teachers really have to embrace it to learn it themselves.
Great question. how much do teachers actually understand about this? How much of their education is sort of neuroeducation?
Yeah.
The answer is powerfully little. Powerfully little. Carroll School does a ton of this kind of teaching of kids. In my retirement, did I tell you I'm not going to get it retirement? I'm teaching graduate students at Endicott College. My course is called Neuroscience in Education. Harvard Graduate School of Education had something called Mind Brain Education. And Kurt Fisher, brilliant thinker in the field, died recently, and Harvard no longer has that program. It's like incredibly frustrating how slow this is to get into brains. I started with the neuromyths. People can dismiss this with neuromyths all over the place and say, it's just another neuromyth. Then we understand how the brain reads. We don't understand it perfectly, but we understand it enough, and I hope I've made this point, to give teachers and parents some sense of direction. Like, don't buy the fact that the 50th percentile, the 25th percentile is a success story. Well, you know, they're scoring on grade level. Well, great. How are they functioning on a day-to-day basis? The fact that you can show me a test score that says they're fine, as a parent, I know they're not fine. The kid knows they're not fine. So, very little. It's really discouraging. This is not part of undergraduate or graduate teacher education. Almost anywhere. Yeah.
Thank you so much. This was very interesting. So, you mentioned the important part about the emotionality and learning. My daughter is going to go to high school next year, and she's quite ambitious and pushes herself. And as a parent, I don't know quite, I'm at the moment where I don't know what to say. Like, should I let her just push herself and get stressed out with a little bit of gentle sort of reminders that she doesn't need to be like X, Y, and Z, and she can figure things out herself? Or do I keep nurturing and protecting and sort of expect a little bit less? When do I stand in this sort of adolescent sort of self-fighting?
Right.
Right.
So the question is about the relationship between our emotional well-being and how hard a child pushes herself. And in the learning kit, I think are a lot of the answers to these questions. This past year, I've taught dyslexic kids my whole life, my whole career. And this is the first year when I had kids who didn't have any diagnosis at all. Some did, some didn't. And even the strongest students who pushed themselves so hard and have always been successful in school could use the language of the learning pit. And so I would go to this wonderful kid named Asher, and he'd go, "Oh, Steve, I'm in the pit right now." And he would figure out how to get out of the pit. His acknowledgement that he was in the pit was hugely important. And I think it's responsive to your question, that he did not beat himself up that he didn't get it. He had learned, I had taught him, that being in the pit is fine. But you gotta find the ladder, you gotta find the rope, you gotta yell for help somehow. So my answer to your question is, I think kids who push themselves really hard, it's part of what effective effort is about. But effective effort as opposed to ineffective effort. Bang your head against the wall is not going to teach you how to read. You might try so hard in a way that doesn't really help you at all. So I think the differentiation that teachers need to understand is, this is going to help you, and I love your motivation. That is not going to help you. And to be able to understand the difference. There's a whole really brilliant, you go to this website from the Efficacy Institute, Dr. Jeffrey Howard, about teaching effective effort. And so when you see kids who are just, and there are a lot of dyslexic kids who are like this, I'm going to get this. You want to make sure that they're doing things that are helpful. So how does a dyslexic child handle a large classroom full of neurotypical kids in terms of emotional well-being? So to me, it's all about the teacher's worldview. If the teacher actually believes that human behavior falls into bell-shaped curves, and it does, you know it does, right? Some people are really good at singing, some people are terrible at singing, and most of us kind of suck. But if you leave it that way, it'll stay that way. So if a teacher believes that in their classroom there are going to be some kids who are just superstar readers and some who are absolutely horrible readers, and most are fine, and they say that's just the way of the world, that's a disaster for a child. If the teacher's belief system is, I will never quit on you, I completely believe in your capacity to get better at this, and effective effort is going to drive you from the bad part of the curve to the good part of the curve, then I think it can really work.
And actually, to clarify, what I meant was as far as an academic approach. So do all these kids just need to go to Carroll and be in a classroom that they're going to do an approach that's for them? Or is an integrated classroom possible in your view? And if so, what does that look like?
An integrated classroom looks non-hierarchical. In other words, if the teacher believes, I'm going to have my 25 kids, I'm going to have the really good readers, and I'm going to have the really bad readers, and I'm going to have a bunch of groups in between, and the kids know that it's set up that way, that's not good emotionally. If the teacher believes this is not a hierarchy of good, average, and bad, but rather these kids need this approach, these kids need this approach, and that the teacher teaches the difference between fair and equal. Equal means every kid gets the same. Fair means every kid gets what they most need in order to thrive. So my answer is it depends on the teacher's belief system, whether it's emotionally healthy for a dyslexic child to stay in a mainstream classroom.
So it really is about emotion more so than it is academic approach.
Absolutely. Absolutely. And then, because the way the brain's organized, if we are scared every time we're facing a reading task, we're not going to be able to get to the academic component of this. We're just going to defend ourselves against humiliation.
Yeah, I thought that TCI data was so compelling, and I'm just curious about it. I have a couple questions. One, I'm assuming, did you tailor the intervention to the particular deficits of those children? And then secondly, did you see it translate into improved reading? And then my third question is that widely available, or is that just an innovation that is at Carroll? My daughter is doing that here for the summer, and she enjoys it a lot. And it sounds like a great idea. Yeah.
Right. So, targeted cognitive intervention, TCI. Targeted means you go at an individual child's specific deficits. And you're sitting amongst people who continue to push this program forward now that I've retired. And it's gotten much more specific, much more individualized, much more sophisticated about addressing a child's weakness. And then these folks, Louisa, Ben, and Jen, are totally psyched and shared with me the 10-year data on what is the relationship between addressing those underlying cognitive issues and their oral reading fluency outcomes. And they're powerful. And so, make sure I say this right, Jen. There is a student of John Gabrielli's, doctoral student, who is going to be taking these data and turning it into her dissertation.
An article,
Scientific article.
publication on.
Is she a postdoc or is she?
She's a postdoc.
Oh, so she's already got her doctorate, and she's taking this TCI data to try to get a peer-reviewed Journal article, which we've been fighting for 10 years. It's incredibly hard to do. It will rock the world. It should rock the world. It should rock the world like those neuroimages didn't 30 years ago. But an article that says you can address these underlying cognitive issues to a very positive academic outcome should rock the world. Probably won't, but it should. Yeah, way back.
This sort of come up in some of your responses. I'm curious, early in the slide when you were talking about the neuromyths and the learning style, I think parents and teachers hear that a lot. Can you just clarify, because even in your answer, it feels a little back and forth. Like, learning style isn't real, that's a myth, but we know children who have strong visual spatial abilities prefer seeing images, so can you just tease that out a little bit more?
Yeah, excellent. I think you all heard the question, right? So one of my gurus, I've never met him, his name's Stanislas Dehaene. He is a neuroscientist in Paris. He wrote the book, How We Learn. And in there he says, the differences in learning style across humanity are so small compared to the similarities in how we all learn, that we don't want teachers to think that I need to focus on the differences. And I have this group over here who needs everything presented visually, and this group over here who should never see it, but should only hear it. And Dehaene's point is, no, these are tendencies or proclivities within individuals. But it's not a recipe for how to teach. You're absolutely right. And Carroll is great at this, of finding the unique strengths within an individual kid and just amplifying those, because that's probably their happiness in life, possibly career-related, possibly having to do with their socioeconomic status in the long term. Those gifts need to be nurtured, but you're not going to do that. So you're right when you say there's back and forth on it. Yeah, we are unique. Each of us is unique. But we're more similar as learners than we could ever imagine. That's the point there.
The physiological level, the biology. What's the timeline it takes for the neuroplasticity rewiring and establishing those neural pathways? You know, physically, you sprain an ankle, you break a bone, 6 to 8 weeks, 12 weeks, you're recovering, right? What's the equivalency of that at a neurological level?
Right. So the question is, how fast can neuroplasticity take over and start to have a major positive impact on a child?
More than 60 hours.
More than 60 hours. And the answer is it's going to be very, very different from kid to kid. But your question is really important. Schools need to know where kids are. They need data. So this is a radar chart. This is something schools don't do. This is a radar chart with all sorts of skills necessary for reading around the outside of it. And they should track very carefully where a child is at the beginning, what intervention they're using to try to improve a weakness, and whether that's making a difference. And so you track it over time. And in the best scenario, like the broken leg analogy, you set it, you take another x-ray of it, you go, this is working. We're starting to see calcium building and we're getting healing. That's what should happen educationally as well. Take this radar, and on this one you say, oh my gosh, look at word identification there up at about 2 o'clock. Or look at reading fluency down here at 8 o'clock. These things are in towards the center, which means they're great weaknesses, huge weaknesses. Well, prescribe the educational intervention and then watch what happens. Oh, we're starting to get some good results. This is what schools don't do nearly with enough sophistication. And we got to the place 10 years ago where we decided as a school, we're going to tell parents the absolute truth. And we're going to show parents slides where things haven't improved much, and other places where things have improved a lot. And collaborate with parents in a triangle to try to see if we can get stronger interventions. So I said we didn't have time to talk about neurodiagnosis and neuroprescription. That's what this is. And I think the field will get more and more sophisticated with this, with your grandchildren, probably be able to say, after 6 weeks, this intervention isn't working. And we see no signs that it's working. Emotionally, it's not sound. Scrap it, try something else. That's the way it's supposed to work. Read my book, which I'll probably never get published. That's what it's about. How about one more, Faith? Yeah.
I understand that gender is a complex issue, obviously. Are there gender differences in the way that dyslexia manifests itself? Or is it just more noticeable with certain kinds of gender behaviors like academic classes?
Right. So, questions about gender differences in dyslexia? No, there are no gender differences. No, there are huge gender differences. Originally, when I started at Carroll, there were 90% of the students were boys. And the myth was, just in neurogenesis, girls aren't as susceptible to reading disorders as boys. And then you realize there's a whole lot of gender bias in that statement, that girls do manifest differently. And so by the time I left Carroll, I think Carroll's about 50-50 girls and boys. Back in the olden days at Israel Hospital, they did sort of like the meat slicer at Stop and Shop. They did cross-section slices of brains and found huge gender differences in the way dyslexia manifests itself in boys and girls. Everything I've shown you today is cross-gender, but I think the remedial implications are quite significant. Here are the tendencies. Boys tend to just really be terrible at decoding and get identified for services, tier 1, tier 2, tier 3. Girls tend to do okay with the decoding part, and teachers in schools go, they're doing great. They're on level in first grade, second grade, where decoding is what it's all about. And then you get into the other aspects of reading, and you see the number of girls identified explode. So lots of interesting issues with gender awareness. But I think with this kind of approach, when you're truly individualizing, there are some girls historically in Carroll who've been the worst decoders, the most difficult to remediate of all. So is that another component of the female manifestation of dyslexia? A lot of research going on there, for sure. So, we're good, huh? Yeah, thank you all.